All right, 7.5, which is definitely the most important section here for Chapter 7. We've done 4 sections now, just learning the Laplace transformation and the inverse. 7.5 is the way to use it. And I know we already saw one example of that in the last section, just real quick, but we're going to see some more today. First thing I want to write out are just some steps to solving these. So what you want to do, of course, you want to take the Laplace transform of both sides of the differential equation. After that, use those properties that we've been talking about, the linearity property, everything, right? All of those theorems that we talked about. The derivative properties come into play too. So use properties and the initial conditions to transform and solve solve for the transform. So remember, you want to solve for the Laplace transformation of the function, then determine the inverse to get the function itself. And here we go, a bunch of examples. So we're going to start off with easy examples, ones that we could have solved using other methods, and then we'll get into more complicated ones where only the Laplace transformation can solve it. All right, so solve the initial value problem, y double prime minus 2y prime plus 5y is equal to negative 8 e to the negative t with initial conditions y of 0 is equal to 2, y prime of 0 is equal to 12. Okay, great. So yes, we could have solved this a different way. This is a second order linear non-homogeneous equation. To solve this, you would find the homogeneous solutions using the auxiliary equation. Then you would use the method of undetermined coefficients to find the particular solution to the non-homogeneous, add all those solutions together to get the final solution. Then you have to plug in the initial conditions to get the constants out of there. But using this this Laplace transformation, we can solve this a little bit easier. So what we're going to do is we're going to take the Laplace transformation of both sides. So we're going to do it of the left-hand side. I'll just write it all out. So the Laplace transformation of the y double prime minus 2y prime plus 5y, and that's going to equal to the Laplace transformation of the left-hand or the right-hand side there, the negative 8 e to the negative t. Okay. Now, we're going to use the linearity principle here, and we're going to take the Laplace transformation of each one of these individually. And when we take the Laplace transformation of the derivatives, we're going to go ahead and write that out using that theorem that we have. So the Laplace transformation of these, how about this? Let's write them out separately. We know we're going to be taking the Laplace transformation of the second derivative. So let's go ahead and write out what that is. Remember, the Laplace transformation of the second derivative, and there's just a formula to it. It's s squared. The Laplace transformation of just the function itself minus s times the function at the origin 0 minus the derivative of the function at 0. Okay, and we can go ahead and substitute the stuff in here, right? So that's going to be the little s squared. The Laplace transform of y, we can't do anything about that. In fact, that's what we're trying to solve for. Minus s times y sub 0 is going to be a minus 2s minus the derivative at 0, which is going to be a minus 12. All right, so that's just the Laplace transformation of the second derivative there. Let's also go ahead and find the Laplace transformation of the first derivative, because we're going to need that as well. This, remember, from the formula is just s times the Laplace of the function. And that's just going to be minus the function at 0. So for us, this is going to be s Laplace of y, and that's going to be minus the function at 0 is that 2. Okay, so now we're going to take all of this and replace this top line right here. So instead of the Laplace of the second derivative, I'm just going to be plugging this term in here, so it's going to be the s squared. The Laplace of y minus 2s minus 12. We have to be a little bit careful here because we are going to have to factor out the negative 2 from the first derivative. So negative 2 times, and then replacing the first derivative with this, s, the Laplace of y minus 2. Okay, and then plus 5 times the Laplace of y. And that's going to be equal to the Laplace transformation of negative 8 e to the negative t. And remember, that is something that we're going to look at the table in the book to find. So just pulling up the table here. Pulling up the table here. We're looking at this, right? We have this e to the negative t for us, and we have a negative 8 out in front. That negative 8 just comes out to the front, and then negative 1 is going to be my a here. So I'm going to have 1 over s, and this is going to be plus 1 since the a is negative 1. Okay, so the negative 8 comes out, and then it's going to be that fraction 1 over s plus 1 for the Laplace transformation of e to the negative t. Again, this is coming straight from the table. I don't know why I put that in parentheses. Okay, cool. Good. So now we just want to clean this up, right? So just use algebra here. We'll distribute the two. We'll combine all like terms together and see what we get. So everything that has a Laplace transformation, I'm going to go ahead and write all that stuff out. We have an s squared from this term. This is going to be a negative 2s, and we're going to have a plus 5. All of this is going to be the coefficient now for the Laplace of y. Okay. We have, what else do we have? We have just an s term floating around. So remember that you want to solve for the Laplace of y. What I'm going to go ahead and do is I'm just going to move everything over to the right-hand side because we're going to eventually need to divide by this anyway. We already have this negative 8 over s plus 1 on the right-hand side. We have this negative 2s. I'm going to add that 2s over to the right-hand side. We have this negative 12, so I'm going to add 12 over to the right-hand side. We also have a positive 4 after you distribute the negative 2, so I'm going to subtract the 4 over. And so I don't have to write a whole new line. 12 minus 4 is 8. All right, so this is just moving everything over to the right-hand side, and then finally we want to divide by this s squared minus 2s plus 5 on this right-hand side here. So we're going to end up with the Laplace of y is equal to, and then this right-hand side is just going to be ugly for a little bit, but we'll clean it up. So you have the option to either divide each of these terms by the s squared minus 2s plus 5, or you can divide the whole thing by that. I think that's how I'm going to go ahead and do it at first here. So we're going to have a fraction. My numerator is going to be what's already over there, the negative 8 plus s plus 1. Oh, that's a 2, not an, oops. All right. 2 should be an s. Plus a 2s plus an 8, so that's all in the numerator, and then we have the s squared minus 2s plus 5 there in the denominator. And we have to clean this up because this does not match anything over there in our table. So to clean this up, I'll factor, can I factor this denominator? Kind of doesn't look like it. Oh, that sucks. Okay, give me a second. Okay, I thought about it for a second. I think what we need to do is we'll just combine all the stuff here in the numerator into a single fraction and then simplify from there. So all of these need to have that denominator of s plus 1. So I'll leave the first one alone, the negative 8 over s plus 1, plus, then we're going to have a 2s times s plus 1 divided by s plus 1. Plus, then we're going to have an 8 s plus 1 divided by an s plus 1. So this is just getting all of these terms in the numerator to have that same denominator. That way we can combine them all together. Okay, so just adding all of these, the numerators of the numerators together. So it's going to have an s plus 1 in the denominator, and then all of that stuff up top, we have a negative 8. I'm going to go ahead and distribute some stuff, so we're going to have a plus 2s squared plus 2s plus an 8s plus an 8. My denominator stays the same, the s squared minus 2s plus 5. All right, so this line here was just distributing out the parentheses, then adding all of those terms together. Keeping it going with the simplification now, the negative 8 here and the positive 8 there cancel out. Also, this s plus 1 here, I can just move to the denominator. You can think of that as the division of a fraction. So we're going to end up with this. We still have the 2s squared in the numerator. 2s and 8s will combine together to be a 10s. In the denominator, I think all I can do is just write it like this. So s squared minus 2s plus 5, and then that s plus 1 comes down. And unfortunately, I think we're just stuck with it like this. Okay, but now, remember that we want to find the inverse Laplace transformation to actually get our solution. This does not match anything in our table, so what we're going to have to do is partial fractions. Alright, so we're going to rewrite this as 2s squared plus 10s. So I'm just copying it down here. And we're going to set this equal to the partial fraction decomposition. S squared minus 2s plus 5, that is a quadratic factor that is not factorable, which means that it's going to have to be broken up into a linear term up top, as plus b, and then just we'll leave it alone, s squared minus 2s plus 5. And that's going to be plus my linear term now, which is going to just be a c over s plus 1. Alright, we have to figure out what these constants are, so we're going to multiply everything by that common denominator. On the left-hand side, we're going to get 2s squared plus 10s. On the right-hand side, we're going to have that as plus b. We're going to multiply that by s plus 1, plus the c we're going to multiply by the s squared minus 2s plus 5. I don't know if there's an easy way to figure out what these are going to be. I think, unfortunately, the best method may just be to multiply all this out and then do the coefficient method. So leaving the left-hand side alone, we're going to FOIL this first thing out. So we're going to have as squared plus as plus bs plus b, and then just distribute the c into this, so plus cs squared minus 2cs and then plus 5c. Okay. At this point, we're going to set the s squared coefficients equal, the s coefficients, and then just the constant coefficients. So I do have some s squareds floating around. I have a 2 on the left-hand side, and then an a plus c on the right-hand side. I have some s terms floating around, a 10 on the left, an a plus b minus 2c on the right. And then I also have some constant terms, 0 on the left, and then b plus 5c on the right. Okay, and then you want to solve the system of equations that we have here. However you feel comfortable solving it, whether you want to use that matrix method that I showed everybody back in 172 or Calc 2 if you took that with me, and then otherwise just do some substitution stuff. So probably from this bottom equation here, I would go ahead and set b equal to negative 5c. This top equation here, if I solve that for a, that gives me a is equal to 2 minus c, and I would plug both of those into the second equation here. So 10 on the left, a is now 2 minus c, plus b is now negative 5c, and then minus 2c. Alright, still 10 on the left. It looks like I only have a 2 on the right, and then negative c minus 5c minus 2c is negative 9c. Subtract the 2 over and then divide by negative 9. Looks like my c is going to be something. Did I mess up here? I'm not getting the same thing I was getting in my notes. Nope, because it can't add, right? That should be a negative 8c there, sorry. Negative c minus 5c minus 2c is just negative 8c instead. Alright, so subtract the 2 over, divide by negative 8, we're going to get c is negative 1. And then if c is negative 1, that tells me what my a is equal to. My a is going to be 2 plus 1, so my a is 3. And then down here, if c is negative 1, that says that my b has to be positive 5. Alright, so then plugging all of that into the Laplace equation we had up top, right? So what we had is that the Laplace of y is equal to this thing here. But now we're going to break it up into our partial fraction decomposition. So it's going to be as plus b, which is 3s plus 5, that divided by the s squared minus 2s plus 5, plus the c over s plus 1, which was negative 1 over the s plus 1. Okay, now we want to go to the table in the book to see if we can match any of these. I'm pretty sure we're not going to be able to match this one until we do a completing the square, but this one at least we should match. So that's going to be an e to the negative t with a negative 1 out in front. Let's go ahead and complete the square for this one. So we still have the 3s plus 5 up top. In the bottom here, we have the s squared, we have the negative 2s. We're going to take half of the negative 2 and square it, which is positive 1. But if we, if we add a 1, we also have to subtract a 1. All right, and then still have the 3s plus 5 up top. Completing the square there in the denominator, we're going to have s minus 1 all squared. That's going to be plus 4. Plus, we still here have the negative 1 over the s plus 1. We may need to split this up into two separate fractions to get this to work, with a 3s on top over this and then a 5 on top over this. Let's go ahead and head over to our table. In fact, let me get both of these on the same screen here. Yeah, so it's definitely looking like we're going to have to split this up because there is not a term that has an s plus anything in the numerator. We only have a constant up top on 1 and then an s minus something here on the bottom. So let's break it up. So breaking it up, and we want to get kind of clever about it. Let's do this. So I'm noticing that I have to have an s minus a in one of the numerators. So I'll break it up this way. Instead of 3s plus 5, I'm going to write that as this. 3 times s minus 1. So basically I just pulled a negative 3 out of the 5. I have to also undo that by adding 3 to the 5 to make that an 8. All right, so the reason I'm doing that is to force there to be an s minus 1 instead of an s. The reason I wanted the minus 1 there is because it has to match the same thing that's down here in the numerator. I still have this negative 1 over s plus 1 as well. Okay, now we'll break it up into the two separate fractions. So we're going to have just 3 times s minus 1 over the s minus 1 all squared, plus 4. Plus, then we're going to have an 8 over the same thing, s minus 1 all squared plus 4. Plus we still have this thing. Okay, good, and then we're pretty much done. So now we can just go ahead and write what it's going to be over top here. So this 3 is going to come out to the front. And then we have the s minus 1 over s minus 1 squared plus b squared. So my b is 2. So this first term is going to be a 3. E to the at, where a is just 1. So 3 e to the t. And then cosine of bt, where my b is going to be 2 from the square root of 4. Plus, so for this term, we have to be a little bit clever because it does need that b up top. And again, the b is 2. So I'm just going to factor out what I need to factor out to force that to be a 2 by factoring out a 4. So the 4 is going to be pulled out to the front, and now this matches this term. So e again to the 1t, and now it's going to be sine of bt, which is 2t. All right, and then minus 1, s plus 1 is coming from this one, where my 1 is going to be negative 1, so e to the negative t there. Good, and that's it. So that is going to be the final answer for our problem. This one took a little bit longer than I wanted it to. Sorry about that. These problems, again, like everything we do in this class, is just going to take a long time. But this, let me copy it, is the solution to what we started with way up top here. If you were to take this and plug it in, the second derivative, the first derivative of the function itself, everything would match up on both sides, and it satisfies these initial conditions. Okay, great. Another example in the next video.